Today we're going to do the Feb March Physics P4 paper. It's 20th April right now, and it's 10:20 a.m. So it should take me about 1 hour. It's actually supposed to be 1 hour 15 minutes, but we'll try to finish it quickly. And let's see. So, hmm. So state the distance between home and school. Okay, so this one is a distance time graph given to you, and a student cycles from home to school. Okay, so this here is the distance. So let's read it. This point, and that looks like 1.55, 1.6, 1.65, 1.7, 1.7 kilometers. So that happens to be the distance. Okay. Hmm. State one point which identifies a time when the student accelerates. Well, we are going to look at a part of the curve, a part of this sketch where the gradient of the line seems to have increased. So it's obviously that BC thing from AB. It is this, and BC it gets steeper. So that is the place where it accelerates. You know that the gradient of a distance time curve shows you acceleration. So it's definitely the state one point which identifies a time when the student accelerates its B. And you see that the steepness reduces from C onwards. So that's where the deceleration is happening. So you put up the point C. Calculate the student's maximum speed in kilometer per hour. Okay, that's a thing. They have given distance in kilometer and time in minutes, but they want the speed in kilometer per hour. Okay. See, this is where you know the student is at its maximum speed. So we are gonna find out the gradient of this part of the whole sketch. So we will go find out the gradient. Uh, so you go take these 2 points and read these values and these values from the x and these from the y. So this one looks like 1.25, and this one is 0.25, zero point 0.3, 0.35, 0.4, and this is 7.5. Okay, so the gradient is gonna be, let's see, let's put it up here. Y2 minus y1 divided by x2 minus x1. Okay, so that's 0.85 divided by a 2.5. Now, we need to see, we are talking about kilometers on the distance and minutes on the denominator here, on the time. So, you need to convert this into kilometers per hour. So, although I'll go and find out the thing in kilometer per minute and then I'll convert it. Or maybe I'll do it right now. I know 0.85 and 2.5 minutes is 2.5 divided by 60 hours. And that's how I know it's going to be 60 multiplied by 0.85 divided by 2.5. And we can mention here conversion. 2 hours. Okay, let's see what it comes out to be. So 20.4 kilometer per hour. Okay, let me see. It feels a little weird for the speed of a student to be 20 kilometers per hour. Uh, let's see. Have I read them right? 1.05, 1.1, 1.15, 1.2, 1.25. That's 0.253354. Okay, 5, 5.5, 6, 6.5, 7, 7.5. 7.5 minutes and 5 minutes, that's 2.5 minutes for an increase of 0.85. Is that correct? Let me check. 1.25 minus a point 0.4. Yeah, that's 0.85. 0.85 kilometers in 2.5 minutes. Okay. Sixty into 0.85 divided by 2.5. 20.4. Okay, 20.4. Uh, that happens to be the speed here. State the equation that links density, mass, and volume. So, you know, density is supposed to be mass divided by volume. Rho equals m by v. And just to be sure, we write the units also. Kilogram per meter cube. M is in kilograms and v is in meter cube. Okay. The density of steel is 7900. The mass of a solid steel is 110 kilograms. Calculate the volume. We know that density is 7900 and it is supposed to be mass by volume. So volume comes out to be 110 divided by 7900 and that will be 110 divided by 7900. A 0.014 kilogram per meter cube. Oh, sorry. That's the volume. So why meter cube? That's your answer, 0.014. Okay. Um, the density of seawater is 1030. State why the solid cube sinks when placed in seawater. Okay, the steel cube has a density of 7900 kilogram per meter cube, which is greater than that of sea water. Explain why the steel ship floats on seawater. Well, that's a very common question. Uh, See, ships which are made out of steel, of course, they have uh, a density more than that of seawater, but they still happen to float. So the idea is for you to know that and be able to explain that the overall density of a steel ship is lesser than that of seawater because steel ships are hollow inside. So steel ships are hollow and contain air. Overall density is less than sea water. That's all. That's what your explanation should be. The mass of the ship is the ship accelerates at that. Calculate the force which causes this acceleration. We use F equals to mass into acceleration. So F equals 3.5 into 10 to the power of 7 into 0.75, and that will come out to be 3.5 into 0.75. So that's 2.6 into 10 to the power of 7 newtons. There. Explain why the force provided by the ship's engine must be larger than the value you calculated. Well, if the thing has to accelerate, you know that drag force, the friction of uh, the water is going to apply a drag force on the ship as it goes, as it moves forwards. So not only do you have to maintain an acceleration of 0.75, you also have to compensate. The engine has to compensate for the work against friction, the drag that it's experiencing. So that is what you want to tell here. Explain the force provided by the ship's engine must be larger. So you tell them engine must provide extra force to work against drag force by water. Besides providing constant acceleration. Drag force increases with velocity. Okay. Hmm. Now, calculate the weight of the polar bear. Well, if the mass of the polar bear is 590, the weight is going to be mass into 9.8, basically mg. Okay. So that is going to be how much? Let's see. 590 into 9.8. That's 5782 newtons. And I can write it as 5782 newtons. Although writing a 5800, rounding it off to 2SF is not wrong. I believe I don't have the marking scheme, but it'll be fine if you put up a 5782. Calculate the pressure that the polar bear exerts on the ice. Well, it's gonna exert uh, pressure equal to force by area. So force that the polar bear applies, it's the weight of it divided by the area. So that's a 5782 divided by the area. So area in contact with ice for the polar bear is 1.12. And that is how you get to a value of 5782 divided by 1.12. 5782 divided by 1.12 Newton per meter square. Okay. So that's 5162.5 pascals. So I can write it as 5163 pascals. Okay. I don't write newtons two times here. Okay. Use the numbers to complete each equation. Each number may be used once, more than once, or not at all. Mass of the polar bear equals dash times mass of person. Okay, so we're gonna have to divide these two. 590 divided by 84. 590 divided by 84. Oh, that's a 7 times. For this one, it's 590 divided by 84. Comes out to be around 7. So that is 7, 7.02. Area of polar bear in contact with the ice is that many times area of person in contact with the ice. Okay, so we're going to divide that area of contacts. So 1.12 divided by zero point zero 0.02. 56 times. And pressure exerted by the person is that many times the pressure exerted by the polar bear. Okay. 8 times, I think. So if you see, the area is 56 times while the mass is only 7 times. Oh, it's 1/8. Okay, let me just check once. Give me a second. I'm going to go simply calculate the pressure exerted by the person. So 84 into 9.8 divided by the area 0.02. Let's see. 84 multiplied by 9.8 divided by 0.02. Oh, that's like way large. 8 times. That's 41,160, and the pressure by the bear was a 5163. So almost a 8 times. Okay, so the pressure, so this guy applies 8 times the pressure. Okay, under the ice is seawater with a density of 1030. Calculate the change in pressure between the top of the seawater and the depth of 2 point. Well, we use the formula. Change in pressure is rho g change in depth. So rho is a 1030. Uh, G is a 9.81 and height is a 2.5. So you go 1030 into 9.81 into 2.5. 25260, and that's a 25260.75, and I can write it as 25300 pascals. I try to be around 2 3 significant figures. 25260 pascals. Okay, so that seems fine to me. Am I missing out on something here? No. Okay. State the method of thermal energy transfer that warms the people. An outdoor heater warms people sitting outside. Figure shows the heater. State the method of thermal radiation, thermal energy transfer, radiation it is. I just want to be safe about it. So I'll put up infrared radiation. Okay. Complete the sentences about energy transfers that warm the table. The heat transfers, the heater transfers energy to the dash store of the table. Thermal energy store. The temperature of the table increases. The rate of energy dash by the table is greater than the, see, if the table, if the if the table is being heated, energy transfers that warm the table. So if the table is being heated, there's only one way. The heat that it is gaining is more than the heat it's losing. So the rate of energy transfer by the table is greater than the heat, the the rate of energy the rate of energy dash by the table is greater than the rate of energy dash by the table. The rate of energy absorbed. I can put up gained also. absorbed or gained by the table is greater than the rate of energy lost or dissipated. And again, I'm not sure. It's supposed to be gained by the table and lost. I absorbed and dissipated just to be close to the marking scheme. One of the people puts a white cloth on the table. Explain why the white cloth causes the temperature of the table to decrease. Well, white is a good reflector. White is a great reflector and a bad absorber. So, table doesn't receive heat at at the same rate. Now, the heater has a power of 2.5 kilowatts. The heater is switched on for 3 hours. Calculate in kilowatt hour transferred transferred electrically by the heater. So that's a power formula. Power is supposed to be no, sorry, energy is supposed to be power into time, where power is supposed to be in kilowatts, time is supposed to be in hours, energy is supposed to be in kilowatt hours. That's the formula you want to use. So 2.5 into 3, so that's 7.5 kilowatt hour. Okay. Atmospheric pressure is this a volume of the meter cube of air at atmospheric pressure is pumped into a car tire. The pressure of the air when it is inside is this. Calculate the volume of the air when it is in the car tire. Okay, so use the formula P1 V1 equals P2 V2. So you're looking at 1 into 10 to the power of 5 into 1.02 equals P2 into V2. And V2 here will come out to be, let's see, 0.39 meter cube. And that's all there is. 0.39 meter cube. Am I correct with a 1.02? Let's see. 1.02 divided by 2.6. 0.39, yes. 0.39 meter cube. Describe the structure of a gas in terms of separation. In separation, their molecules are far apart. Arrangement, it's random. No fixed structure. I just want to be sure, so I'll say distance is larger, is very large compared to the size of the molecules. But this is a little. Uh, I don't think it's required, but I'll still keep it there. Molecules are far apart should be more than enough. Arrangement random should be enough. Motion, it's again random and rapid in all the directions. No fixed trajectory is how I will keep it. Okay. Explain in terms of particles why the internal energy of the gas decreases when the gas is at a lower temperature. Well, temperature is the measure of average kinetic energy. If there is lower temperature, there is lower kinetic energy. So you write temperature is measure of average kinetic energy. Low temperature means low kinetic energy. Internal energy depends on kinetic energy, and that is how you know low temperature, low kinetic energy, and low internal energy it will be. Okay. That must be 2 marks. I hope it's 2 marks. Let's see. Okay, so figure 6.1 is a full scale drawing of an object, a thin converging lens, and the image I. Identify Z. Okay, so identify Z. Z is the principal axis. That's what you call it. That's your principal axis. And what else do they want? Determine the focal length of the lens. So I'm going to go use the laws of uh, that we already know, laws of refraction through lenses. So if a ray of light goes through the center, it goes undeviated. So there, and if it is parallel to the principal axis, it has to cross through the focus. So there, that's the focus. Okay. And then you want to calculate the focal length. Well, I don't have a ruler to calculate it. Must be some uh, centimeters. I don't know. Determine the focal length of the lens. Show any working in the space provided or on the figure. Show any working in the space provided or on the figure. Well, we just did that. That's where focal length must come out to be about 3 centimeters. I think so. 1 or 2, maybe 2 centimeters. I don't know. Somewhere around that. You need to measure from here to there. That's the length you want to measure. The image is inverted. State 2 other characteristics of the image. Well, one thing's for sure that the thing is real. And about the magnification of it is something that we're going to have to see. So we can actually use a ruler to figure out the magnification if there's any. So there, it's almost the same size. Oh, okay. So that means that the object is at 2 times the focal length, and I think that is also something we can observe. I think it's. I think let's calculate this length. Let's just there. This is the focal length for us. Let's see if the object, the image is at 2 times the focal length. It looks like it is. Oh yeah, so the object is at 2f. Hmm. Okay, so it's gonna be the same size as the same size. as the object. Focal length about 2 centimeter. It feels like this length and this length is the same. So if it's 2, this is 2. So this image looks like it's at 2f. This object looks like it's at 2f also. And that is why the image and the object are the same size. And that's what it feels like to me. I don't have a ruler to say, but I'm pretty sure when the objects are at 2f in front of a lens, the image is also supposed to be the same size. So that is why I think there is no magnification at all. Figure shows a different converging lens with a focal length f. Okay. Draw an X on the figure to show the position for an object which produces a magnified image. Well, you know that a magnified image is produced when the object is between the lens and the focal point there. So you can keep it somewhere here. There. That is where the object should be for it to form a magnified image. And put a tick alongside the two statements which describe the position of the magnified image. On the opposite side, no. On the same side, yes. The same distance from the lens, no. Closer to the lens, no. Further away from the lens, yes. That's correct. So the image, is usually formed somewhere here. Further away from the lens and magnified. Okay, so that is what it is supposed to be. That is why. On the same side of the lens and further away. That is what it is supposed to be. Let's see. The switch is closed. The reading on the voltmeter is 9 volts. The reading on the ammeter is 4.6 milliamperes. That's again a thing to pay attention to. That's milliamperes. So you should know it's 4.6 into 10 to the power of minus 3 amperes they are talking about. Okay. Now, determine the EMF of one cell. Well, there are two cells and 9 volts is the reading on the voltmeter. Well, that's basically if the voltmeter is connected on those two terminals, it is actually telling you the EMF of the battery there. If the voltmeter was connected to one of the components like that, I wouldn't have said it is telling me the EMF of the battery. But since it is connected on those two terminals, it's actually telling you the EMF of the battery. So it's telling you a 9 when there are two cells in that battery. So of course, the EMF of one cell would be 4.5 volts. There are two of them, right? Giving you a 9. So each one of them is going to be 4.5. Complete the sentence to define electric current. Electric current is the amount of charge passing a point per unit time. Okay, the resistance of the fixed resistor is 480. Okay, so this thing is 480 ohms. Calculate the resistance of the thermistor. Okay, this is a 4.6 into 10 to the power of minus 3, and this is 9 volts. What do I do here? Okay, let's calculate the combined resistance of these two. I say that it's X on the resistance of thermistor. So the combined resistance is 480 plus X. And I know that current into resistance should be the voltage. So 9 equals 4.6 into 10 to the power of minus 3 into resistance. Okay, so let's calculate. 1476.52. I can write it as 1480 ohms. Okay. Yeah. 1480 ohms. The thermistor is placed in a beaker of ice. The temperature of the thermistor decreases. State how this change in temperature affects the readings on the voltmeter and the ammeter. See, voltmeter is connected on those two terminals. Whatever happens uh, to the resistance or the temperature of the thermistor, it is not going to change the overall voltage. Okay, so if it's 9 volts provided by the battery, these guys are still going to get 9 volts for sure. That's going to be no change in the voltage. That's the EMF of the battery. EMF of the battery is independent of what's happening inside the like what happens to the resistance of the components. So that's a 9 volts for sure. Nothing's going to change there. But of course, the ammeter reading is going to change because I'll tell you why. Wait. Uh, State how this change in temperature affects. Well, no change to the ammeter reading. But the since the temperature has decreased, the resistance will increase for the thermistor. If the resistance of the thermistor increases, the overall resistance increases because these two are in series with each other, and that's why the current will actually drop. Okay, so that is what you want to say here. So the current, and by the way, they are supposed to tell you the readings, affects the readings. So the uh, reading is what you're gonna tell them about. So the current reduces. So lower reading value observed is how I would want it to be. Okay. They didn't ask me to explain, only state. Okay, fine. A transformer steps down. But what time did I start though? 10:20, I think. Okay, so I've got 35 minutes left. Yeah. Okay, a transformer steps down high voltage electricity. The transformer has six in the primary and the output is for calculate the input. Well, we use the formula N1 by N2 equals V1 by V2. So you go 6200 divided by 43 is supposed to be V1 divided by 230. Common mistake here is substituting the values wrong. So 230 is the output, so it's supposed to be V2. Number of turns on the primary is N1, 6200. Okay. So you go calculate V1 from here. 6200. That's about 33162.79 volts. I'll put it up as 33,000 volts. Maybe I can change it to 33200 volts. That looks all right. 33200 volts. Okay. A 2.2 kilowatt kettle is connected to the secondary coil of the transformer. Okay. Calculate the current in the primary coil of the step down transformer. Assume the okay. So from this from this and that, I will calculate the current in the secondary coil. Well, the power is supposed to be V into I. So 2.2 kilowatt. So that's 2200 watts is equal to 33162.79 into I. That gives me the current in the secondary circuit. Current in the secondary circuit, I2. Okay, let's see. 2200 divided by, so that's 0.06634 amperes. And then I'll go use the formula N1 by N2 equals I2 by I1. So there's an inverse kind of a relationship. Unlike voltage, N1, V1, N2, V2. Here you're going to have N1, N2, I2, I1. Okay, so that's an inverse kind of a thing. So that's something that you want to remember. And then we're going to fill up the values. Now that's 100% efficient. So, of course, there's nothing lost. Number of turns 43 equals I2, that whole value. 0.066 divided by I1. So I1 comes out to be 4. That's a point double zero triple 0.04601 ampere. I'm going to write it as 4.6 into 10 to the power of minus 4 amperes. Hmm. Okay. Am I running out of time though? 9, 10, 11, and that's the end. So I've got 1, 2, 3 questions left. Power station produces 1.3 gigawatts of electricity. That a transformer at the power station steps up the voltage. This reduces the power. State the equation. We use P equals I square R. And explain how the step up transformer reduces power losses during electricity transmission. See, standard answer for 100% efficient power transfer, V1 I1 equals V2 I2. So current and voltage are inversely related when power is constant and power is proportional to I square. No, I shouldn't write it like that. I think I should be a little better. Wait. I'd be like, power is proportional to I square to reduce power loss. Reduce current when power is transmitted at 100% efficiency V1 I1 equals V2 I2. So voltage is inversely proportional to current. To reduce current, voltage is increased. Step-up transformers let the voltage be increased before transmission. Step-up transformer enables the increase in voltage before transmission. That's a better thing to write. We'll write it like that. Step-up transformer enables the increase in voltage. That's how. Power losses is proportional to I square. To reduce power loss, reduce current. When power is transmitted at 100% efficiency, V1 I1 equals to V is inversely proportional to current. To reduce current, voltage is increased. I think I'm being a little extra here, but I just want to explain everything there is for you to understand here. So you may want to reduce a few points here if you want to. I mean, you can simply go um, when power is constant. Power when power is constant, losses are proportional to I square. To reduce power loss, reduce current. V is inversely proportional to I at power equals constant. So increase voltage to reduce current. Step up transformer enables you to do that. Something like that. Okay. What do we have here? A figure shows a beam of alpha particles, and between the two, draw the path of alpha particles inside the electric field. Well, alpha particles will go like that. Hey, sorry, they're supposed to go towards the negative plate there. Okay, and label this alpha. Okay, so I'm gonna label this alpha, and inside the electric field, so gamma particles are gonna go straight. So I'm gonna put up gamma there. Okay. Student places a sheet of paper in the path of the beam before it reaches the electric field. State how this affects the path of alpha particle. You put up a sheet of paper. How this affects the path of the alpha particles and gamma radiations inside the electric field. Well, alpha particles are stopped by the sheet of paper. Do not enter electric field. What about gamma radiation? Well, they pass through the paper and no change in direction. A beam of alpha particles and is replaced. The beam is replaced by a beam of beta particles. State and explain the path of beta particles in the electric field. Use ideas about electrostatic force in your answer. Statement: they are deflected towards the positive plate. P. Explanation: We tell them beta particles are fast moving electrons. They are attracted by the positive charge. And I think fast moving electrons negatively charged they are attracted to the state P. Because opposites attract, opposite charges attract. That must be it. Okay. Complete the sentence about a planetary nebula. Stars expand when they run out of hydrogen to fuel nuclear reactions. A dash forms a planetary nebula. See, a planetary nebula is formed after the a red giant, and that's basically after the death of a star. That's when it becomes a nebula. So the a red supergiant is what we are expecting it to be. A red supergiant actually converts into a planetary nebula, and details of these, you don't have to go search for these things on the internet because they are very vague. But a good thing is, what they want here is something they have already mentioned in the syllabus. So when you go to space physics part of your syllabus, you will see they have mentioned uh, details about these objects, these planetary nebula and all. They want you to write things in specific, and they have clearly mentioned those in the syllabus. So state what is at the center of a planetary nebula. Well, you have a neutron star or a black hole. Well, that's what I remember. It is at the in the syllabus. Mm, there can be white dwarf written in places, but I think it's neutron star and black hole in the syllabus. That's what I think it is. I hope I'm right here. Let's see. We'll go and check. Planetary nebula emits blue light and red light at two specific. Explain why the light with a wavelength of this is the blue light. Hmm? Explain why the white light with a wavelength of this is the blue light. Okay, because smaller wavelength, larger frequency. I think. Explain why the light with a wavelength of this is the blue light. Because blue has wavelength smaller than that of red light and has higher frequency. I I think let's see, because the speed of light in a vacuum is this. Calculate the frequency. We use the formula V equals to F lambda. So 3 into 10 to the power of 8 equals F. F is what we are trying to find. Wavelength is 5.0 into 10 to the power of minus 7 Okay, so let's see. So F comes out to be zero point 0.6 into 10 to the power of 15 hertz. We can write it as 6 into 10 to the power of 14 hertz. Okay. Still, I'm a little confused about these two though. But I remember this is there in the syllabus. So chapters like these, which have been recently added, no syllabus is a good way to. Syllabus is one nice way to memorize the facts instead of going random. Although we have it on the checklist, the Google Sheet I've mentioned, but did not say that the thing goes in circle. So my explanation of it starts from the, uh, uh, if you can see there. Uh, my star, the life cycle of a star that I have mentioned in the checklist is uh, from a nebula to a black dwarf. Okay, and from a nebula to a neutron star or a black hole, they're saying. So you see how nebula is at the beginning of the life cycle and the end of the life cycle. So that is where we are when red supergiant explodes, and what remains is a nebula. May have a black hole or a neutron star at its center. Okay, so that was basically my thing. Let's see. Mm, okay, what is happening here? Am I running out of time? No, I have 15 more minutes. The average orbital speed, define the terms r and t. So r is the distance between the center of the object and the center of the sun. T is the time required for one complete revolution of the object around the sun. Okay. Explain why orbital speed is an average value. You see, um, orbital speed keeps varies when object is closer to sun. It increases and decreases when the object is far away. So the speed that you calculate is average. So speed of 9600 meter per second is the average of all the values of speed. That's what I hope it is. Explain why the orbital speed is an average value. Okay, Saturn is 1.4 into 10 to the power 12 from the sun. show that one Saturn year is approximately 30 Earth years. Okay, so I know that the orbital speed is 9600. So we use the formula V equals to 2 pi r by t. So 9600 equals 2 pi 1.4 into 10 to the power of 12 from the sun, that is the distance, divided by t. Now, t here comes out to be, let's see, 9600 divided by 2 pi into 1.4 into 10 to the power of 12. Hey, no, doing the wrong way. It's supposed to be 2 pi into 1.4 into 10 to the power of 12 divided by 9600. That is it in seconds, if you can see. Now we're going to have to convert it into years to see if it comes out to be 30 years. Okay, so let's see. So time would come out to be whatever that is in seconds multiplied by 1 by 365 into 24 into 60 into 60. So that must come out to be around 30. Let's see. We got 365 into 24 into 60 into 60 into 9600. Okay. But I am not getting it. Uh, okay. So, okay, I've got 10 minutes only. 365 into 24 into 60 into 60 into 9600 divided by 2 divided by pi divided by 1.4 divided by 1,000,000,000,000,000,000,000. What is going on? So what am I doing with that though? 365. What am I converting it into? Okay, hold on. I need to be a little better at this. How many seconds do we have in a year? 365 days, 24 hours, 60 minutes, 60 seconds. So time is, the Saturn is 1.4 into 10 to the power of 12 meters from the sun. V equals 2 pi r by t. T comes out to be these many seconds. Okay, so I'm going to do the calculation now. Let's see. 1.4 into 2 into pi. So that's basically 8.79 into 10 to the power of 12 divided by 9600. comes out to be. Yes. So that's equal to 29.05 and roughly 30 years. Okay, so I've got 8 minutes left. Okay, I hope. I'm a little doubtful about uh this one and this one. But I saw it on my checklist. I think neutron star and black hole I think is correct. Let's see. I hope most of my answers are correct. Mm. And we'll revisit this paper. Okay. Um, that's what it seems. It seems like I'm correct in these questions. Is that 1.7? Yes, it is. Kilometer, minute, 20 is the speed. Have they mentioned anything about significant figures here? Let me see. Mhm. Even this one, same size as the object is something I would want to check because I don't have a ruler to actually claim it to be true, and I don't remember it for sure. The object must be at 2F to have its image the same size. That's what I remember. Let's see. That's it for it, and we'll come back. I'll see you. Bye bye.